still out there drinking their coffee or eating the pastries and filtering through the back. I'm Britton Plord, and it's a great pleasure to be here today. I'm coming from Syracuse University in Syracuse, New York. I'm a professor there in the physics department where I work on low temperature experiments using superconducting circuits. And I'm also, as of January of this year, the editor-in-chief of the IEEE Transactions on Applied Superconductivity. I didn't actually have a chance to look at the movie beforehand, so it was actually a very nice presentation, so my remarks might be a little bit redundant here. But I was just going to say just a little bit about superconductors and their impact on the topic of our panel for right now on electronics and computers. So of course, superconductors have many attractive features. Low loss, Meissner effect, these sorts of things. But in the world of electronics, some key areas these impact. One that didn't get mentioned in the movie this morning was the possibility of doing ultra-sensitive detection of light for future photonics applications and communications. But then also applications in the area of computers involving Josephson tunnel junctions and also microwave circuits. So with Josephson junction-based circuits, you can make classical logic that has extremely low power dissipation. And I'm sure we'll hear some about that in the discussion today in the panel. But also an area that is very close to home for me is using superconducting circuits, Josephson junction-based devices, to make structures that can behave like artificial atoms and follow the laws of quantum mechanics. And this is right now one of the leading technologies to try to build a quantum computer at some point, which is a device that is a system that could not just go faster, but it could solve problems that are completely impossible to solve on the fastest supercomputers that we have available to us today. So all of these applications that I just rattled off here in just a minute are all strongly represented in New York State, and we also heard about some of that highlighted in the movie this morning. In academia, there's many different labs, including mine at Syracuse, also in Rochester, Stony Brook, Cornell, and Buffalo, and others. And then in the industrial side of things, there's very strong intensive efforts at places like IBM and at Hypers and others. And to make these sorts of circuits requires a lot of infrastructure. So in my part of the state, in central New York, my group makes heavy use of the Cornell Nanoscale facility, which is just down the road from us. And of course, here in Albany, we have the great CNSE. In Syracuse, and New York State in general, we're also fortunate to have some of the real key players in cryogenics technology for getting the sorts of cooling power that we need to get down to the very low temperatures where our experiments operate. Just down the road from us in Syracuse, we have Cryomech. It's one of the world-leading manufacturers of the pulse tube coolers that go on most modern-day dilution refrigerators. So I think that was about all I was going to say. But let me now start just by introducing our panelists. I won't go through their bios. You can read these in the pamphlet that you have. I know everybody, but let me just make sure I have the list of names here. So I'll go from your left to right. So we have Oleg Mukhanov from Hypers. We have Jerry Chow from IBM, Yorktown Heights. We have Michael Fancher from CNSE. Michael Hennessy from MTech Labs. And Roman Sobolevsky from University of Rochester. And so I think maybe I'll start out as in the last panel and let each of the panelists give some introductory remarks. And then we'll take questions from the audience. I have a few questions of my own, but we'll sort of let it go from there. So let's maybe start out here with Oleg.
Okay, my name is Oleg Mukhanov. I'm CTO at Hypers Incorporated. Hypers is located in Westchester County, New York, just 30 miles north from New York City. So we are a company, electronics company, which dedicated 100% to superconducting electronics. And of course, it's very difficult to compete against semiconductor electronics, especially I'm talking here while at CNSE, where you see a cutting edge of semiconductor electronics being made here. So in order to survive, we need to identify high-value targets, and also something, as Britton said, something that otherwise cannot be done. And turns out that there are a number of applications that can be only done efficiently or done at all using superconductor electronics. And one of them went products at Hypress. This is voltage standard. It's used for metrology applications. So the volt is defined using Josephson effect and Josephson junction circuits. And we sort of went through A to Z and now selling voltage standard system, cryo-cooled or refrigerated as better word for that. Because cryophobia exists in superconducting electronics very much, and we have to also use all kinds of language skills in order to make it easy to customers to accept. But their acceptance at the end of the day dictated by performance. So you have to show them performance which cannot be attained otherwise, and they will accept that, even despite of the cryogenic nature of our technology. So with this success, we developing a host of other applications, starting from, let's say, RF receivers for satellite communications, where very high frequency satellite communication signals are being received by receivers and digitized without any down conversion into digital stream. So these systems we try to again build, and they were successful operating, and several systems deployed in Department of Defense organizations. And again, perhaps something similar to what you heard at the previous panel. Armed forces were first to accept that because they're more inclined towards achieving high performance than perhaps looking at the cost. Of course, cost is important, but high performance for them means edge in the situation where survival is basically the question. There are a number of other applications. MRI is one of them. Although we're not looking into magnet side of it, we're also looking at the RF or a sensor side of MRIs. It turned out that superconducting electronics can greatly improve MRI machines by making RF side of MRI more sensitive and better to have, which will translate into better image. So doctors, again, might be very happy to see the outcome of using superconductivity in this side too. Superconducting electronics always was considered as perhaps the most promising technology for high-end computing. Starting back from IBM time in 70s and 80s when there was a big program there. So this dream hasn't been lost. Although it was put away a little bit by Moore's law, a great success in semiconductors. But what's happening now is that energy efficiency came to play very prominently. So now what happened that next generation computers are, the dominant metric for them is energy efficiency. Unless new generation of technology will be energy efficient, next generation of computing, exascale computer cannot be done. That's one thing. Another thing, that the cost of energy is so high that Facebook, you may not aware of that, they're building new data center in Arctic Circle, next to the Arctic Circle in Sweden. The reason for that? Because cooling infrastructure is way cheaper there, number one. Number two, there are hydroelectric power stations in close proximity, which are, I think it's about double capacity of the Hoover hydroelectric plant in Nevada. So that's how much energy you need for data centers. Now all business, not just Facebook, all business, banking, everything, airlines, they all reside in this internet layer. So unless we take care of energy efficiency of that, we all will be dependent onto computing in a very critical way. So we believe that superconducting electronics can provide a critical improvement in energy efficiency and solve this issue of next generation computers, data centers, and so on and so forth.
Good, thanks. How about Jerry?
Chow. I'm from IBM Watson Research Lab, where I work in the quantum computing group there. And at IBM, we're embarking on the challenge of building a quantum computer using superconducting circuits. So Britton touched a little bit on what quantum computing is, but basically we can think of quantum computing as a very different paradigm from your computers today. So your classical computing systems, the unit of information is a bit. So these are zeros and ones, and we all know about transistors and semiconductor technology. The quantum computer is based off of qubits or quantum bits, and these qubits can basically be, say, the spin of an electron or energy states within an atom or a molecule. Or in the case of superconductors, it can be energy levels in an artificial atom that is generated by Josephson junction circuits. So what is the benefit of these quantum computers? Well, it turns out that due to quantum mechanics, you can actually make states, which are superposition states between qubits, and you can entangle qubits. And it's really the ability to make these entangled states and superposition states where you can actually apply operations on many qubits in parallel. And by applying operations in parallel, you can actually end up doing certain algorithms where you have a speed up over classical implementations. So probably the most talked about speed up is an algorithm known as Shor's algorithm, and what that is based on is for basically breaking encryption. It lets you factor numbers much faster, exponentially faster than any classical computer. So Shor's algorithm is one of the major drivers for quantum computing. Other applications that have been proposed include faster database searching, as well as simulation of quantum mechanics. So you can actually simulate quantum chemistry systems, for example. So underlying all this, though, is basically the challenge of finding a system which lets you build this quantum computer. And so I already mentioned that there are many different candidate objects for qubits, so such as electron spins, such as molecular ions. These all have different challenges towards building a quantum computer, but the main ingredients which you need are essentially the ability to maintain what's known as quantum coherence. So you need to be able to initialize an excited state of your qubit and not have it relax too fast. And you need to be able to generate a coherent state. So you need to make a superposition state. So you're both in 0 and 1 at the same time, and you want that to last for a long time. So historically, the best systems for this have been the very small and isolated systems, such as in NMR or in atomic systems. These have very long lifetimes. This is why we build our atomic clocks from such systems. But they have the issue of not being very difficult to scale up in the sense of placing many of them together. What's nice about superconducting circuits is that you can use the standard fabrication techniques that we have, EV lithography, and just place many circuits on a chip. And so scaling up is actually a lot simpler. The challenge there is you need to be able to still decouple them from the environment to preserve this idea of coherence. And because these are quantum systems, they want to couple to pretty much everything. And you need to really understand the system, try to decouple them, and preserve these quantum states for longer amounts of time. So for superconducting circuits, the magic element that we use is a Josephson junction, which is generally aluminum oxide. And this serves as a nonlinear inductor, which we couple with sort of standard circuit elements, such as other inductors or capacitors. And we're just basically building circuits of oscillators, anharmonic oscillators, using these Josephson junctions, in which we end up basically separating out two levels to act as our qubit system. And so currently the state of the art is the ability to really couple about a handful of these, 3 to 5 of these qubits on a chip, generate entangled states, and demonstrate some simple quantum algorithms. moving forward, what we'd like to be able to do is build a fault-tolerant system in order to actually run things such as Shor's algorithm or database searching. You need to build a much larger system which has fault tolerance built into it. And the way that is using quantum error correction. And so there are many different schemes for actually making these larger systems of multiple qubits to use quantum error correction. And that is still an outstanding challenge. And so at IBM, what we're actually embarking on is a larger system of about 100 qubits in which you can actually test these principles of quantum error correction. And from there, actually have an idea about whether we can scale this further to a much larger system in which you can have many logical operations and do something that your classical computer can't. So.
Yeah, thanks. Mike?
Sure.
First, I congratulate you on the panel you put together in that order. Following IBM, Hyperis and IBM is perfect. My comments are not going to be focused so much on the specifics of the technology and superconductivity, but more on the transitioning your research into commercial success. And I think we can take a great lesson from IBM in doing that, particularly when you look at how IBM has confronted the increasing challenges of maintaining Moore's law. It has adopted a number of different new paradigms. One, of course, open innovation, where they've teamed up with a variety of other computer chip companies to tackle the development of what's called a common platform. But underlying that has been really the flow of their technology coming from Yorktown, Almaden, and Switzerland, flows into the center here at the college, where it's brought up to first level demonstration, what's called pre-T0. And then it's taken back down to Fishkill, where it's brought up to full yield and with design and modeling kits and everything, and then fanned out to the common platform. Now, why is that important? Well, when you look at the structure of the center here, it is parallels that, in that it is flexible. It allows for and is designed for demonstration of new materials within a established process flow, which is, and that process flow is focused on complementary metal oxide semiconductor devices, which has been driven by ever smaller architectures, but also driven by the introduction of new materials. And that's been required to overcome the physics challenges of speed and heat and what have you. So one data point that I think is important for you to understand is in 2005, the International Technology Roadmap for Semiconductors, the ITRS, which has always was established by the industry to help identify a shared vision of challenges. And that's really what this conference is about, is to try to aggregate a shared vision within each of your application spaces for superconductivity. And that roadmap is characterized by adding a whole nother segment to it called More Than More. So More was the continuation of Moore's observation, not law, it's an observation. But More Than More was the addition of the other, let's call it heterogeneous structures, heterogeneous materials that interact with the environment. So we're really talking analog here. So the More is digital, the More Than More tends to be analog, and it covers everything from power electronics to biochips to RF to all of the fun things. Well, okay, that's a nice thing, but think about the iPhone coming out 2 years later. Was that an accident that it just happened to be within a couple of years of when the ITRS changed? What also happened in that year? It was the year the industry went from a node from a 90 nanometer to a 65 nanometer node. And when that happened, they were able to fold the RF device within the same process flow of the logic device. So now suddenly your power consumption, your form factor, everything was ripe for a company like Apple to come along and put it all together. We also had standardization of the Bluetooth. That was timely. And so within 5 years now, it's completely changed the entire focus of the semiconductor industry away from video games and keeping our 13-year-olds happy to focusing on smartphones. And you're seeing it ripple through the industry. Global Foundries was AMD, it became Global Foundries, so more flexibility in manufacturing, more broadening of the kinds of devices you're going to be making. So why is that important? Well, when I look at our line over here, we have all of the leading computer chip companies here, and they're looking at emerging materials being introduced into this line. And they're looking at two different areas. One is magnetic materials, and the other one is photonic materials. Now, if we were to look at photonics, there's real mainstream things they need. They're running into challenges at the 7 nanometer structure. They're looking for new tunnel materials for just signal propagation. But what happens is the supply chain, the equipment suppliers and material suppliers start to invest in that area. So now you're developing the capability to deposit materials on industry scale 300 millimeter wafer technology. Same thing in magnetics. We heard talk about the quantum effects and mastering that. Well, in the magnetic area, which we're getting closer now to superconductivity, you're looking at your spin transfer torque random access memory, or STT-RAM. Why do you need that? Well, your computational speeds are reaching such a level that you need some cache memory so that you can start to incorporate that on chip, not transfer it off to another memory storage, but do it right within your embedded device. Just like when the iPhone came about, you embedded RF with your CMOS. Now we're embedding more memory, more faster memory within that. So the point of my comments is that I think the key is to try to figure out how you can leverage that backbone CMOS platform. And with the emerging, what's now readily available now is 3D wafer scale packaging. So now you can start to think of your superconducting sensor and having that, the speed of which it operates. You're now able to start to take advantage of the speed of operation that superconductivity achieves. And I think oftentimes when you look at the technologies, sometimes they're just ahead of their time, right? They're incredible technologies, and we've heard every 5 years that superconductivity will be here in 5 years. Well, I think it's kind of patiently waiting for the rest of the technology, the design community, the processing capability, the packaging capability. Those other things have to catch up. And I think, well, I'm not going to say any more about the specifics to the applications. I think what we do here is superconductivity offers a step change in sensitivity. It offers a step change in RF electromagnetic spectrum. And I think being able to integrate that, heterogeneous integration with that CMOS backplane is a very compelling business case that can gather investment. And the college, we spend an enormous amount of time putting together those teams of companies, just like IBM did in 2001 with a common platform. And those teams of companies can be multiple applications or users, if you will, and multiple suppliers. So we heard Pradeep talk about that integration. I would just emphasize, if you don't have the supply chain with you, you're going to be standing out there running out of the castle with the drawbridge pulled up behind you. And you got to bring your supply chain with you. Otherwise, you're going to have a much harder challenge in the marketplace. And I think one of the nice things is the college is set up just for this purpose. Putting aside all of the technology, it's really designed to try to create a neutral environment where partners can protect their IP, but find a common shared vision or roadmap for that area. So I'll conclude my comments there and leave it at that.
Thanks. Hey, Mike.
I'm Mike Hennessy from Nanotech Laboratories. We're a small company located near Global Foundries up the Northway, next to 12. We are a small company with roots, or I should say technology, coming from our past actually at GE R&D Center. My colleague Oddvar Mueller was there working on MRI-related things, and he started something called cryopower. Sometimes they call him the father of cryopower. And myself, I came from intermagnetics, and we had a laboratory at RPI and interacted with them for several years in basic MRI studies from magnet design all the way through to the actual image formation. So it was a great experience. We're taking those technologies and now moving them ahead to other things. And what we have done is utilize some of that capability in merging superconductivity with semiconductors and other electronic devices. We're basically an electronics company, and we really like to have electronics behave well. And what we have found, I think most of you do, is the enemies of electronics are two. One is power, or heat, we should say, and the second is noise. And when you go to cryogenics, both get less, and that's why we like it. We have been working on this for over a decade, and for example, we have been funded by military for doing some of this work. And the power levels range from megawatts down to picowatts. I'll explain that in a minute. In the megawatt areas, we're looking at things like all-electric airplanes, all-electric ships, and that sort of thing. And we're working with the Navy and with NASA on those programs currently. We're also looking at high-power switching for accelerator community with the Department of Energy and utilizing cryogenics to make those switches work better. Because of our MRI background, it turns out that manipulating these quantum spins that Jerry was talking about fit right into the kinds of, I should say, technologies that we've been associated in the past with. And so we're interested also in the very low level detection and the cryogenic electronics of smaller things as well. The basic underlying thing that people have talked about here, and you hear them every once in a while say it, is quantum mechanics. And if you look at all the things we're doing, from the semiconductor realm to the superconductor realm, it really is a demonstration of how quantum mechanics have impacted the society in a very, I should say, under the radar mode. And we have, as a consequence, really been promoting quantum mechanics to everybody. And we have a separate organization, not a distributor, but a subdivision which works on movies. And you saw it today in Tech Studios, and we do a lot of educational things like that with respect to quantum mechanics and other things. And we also use it to explain and promote, businesses and technology in businesses, to explain it simply. And we think that's a very important part of any technology is communicating, and we like to do that. So currently, we have, as I said, been looking at things like the all-electric airplane, the all-electric Navy, and another thing, the futuristic data centers. We've been looking hard at that. And in that concept, you merge both the superconductivity power transmission and power conversion with things like the quantum computers. And really, you talk about efficiency in computing, that is the ultimate long-term goal. And we've been seriously looking at this with the NSF and others and projecting what could be saved in these areas. In this venture, NYSERDA has been very good in supporting these things with us and others. And I can't underline or understate or overstate their support, because without them, a lot of the programs that we deal with wouldn't be possible. So that'll wrap that up then. Thank you.
My name is Roman Sobolewski, and I'm a professor of electrical and computer engineering, physics and material science at the University of Rochester. I'm also a senior scientist at the University of Rochester Laboratory for Laser Energetics. I've been involved in superconductivity for a long time, working both on physics of superconductivity and superconducting devices. but what I consider my major contribution to the area has been championing so-called superconducting optoelectronics and trying to merge superconductivity and optical systems by designing electrical to optical transducers as well as optical to electrical transducers, which could work and connect, let's say, between the fiber optical systems and superconducting electronics. So that was my area and my interest is the certain overlap between optics and predominantly ultra-fast femtosecond optics and electronic digital circuits, and then at the same time studying and understanding optical properties of different materials, including photoresponse of superconductors. And that led me to my most recent work together with a group of Professor Gregor Goldsman from Moscow State Pedagogical University in Moscow. We developed a new type of single photon optical detector, and that's a superconducting detector. It's an interesting concept in the sense that, as I always stress, properties of that device come intrinsically from its nanostructure. And the physics is relatively simple, and the concept is simple. You have a superconducting nanostripe, which is thin enough and narrow enough that impact of absorption of even a single photon, the energy of, let's say, on the order of 2 electron volts, is enough to ruin superconductivity in that nanostripe. And this way you have a large global, this few millivolt signal, which you can readily detect. And the device response time depends on the design, will be from tens of picoseconds to a few nanoseconds. So you can have a photodetector operating in a range from at least 200 megahertz all the way to a few gigahertz for telecommunication. Basically no dark counts, well, it's a superconducting device working at low temperatures. No after pulsing. After all, it's essentially a passive device. It's a piece of metal which is in superconducting state and switches into resistive state, temporary switches into resistive state. So it's a very good. It allows to count photons in infrared, not only optical visible light photons or X-rays, but also in infrared. So currently, it's been established as the best currently available high-performance device for primarily optical communications, quantum cryptography, which tries to make quantum computers obsolete even before they are actually being fabricated. And this area is growing into other applications in terms of single molecule optical tomography, anywhere where you need to have a performance of a very sensitive optical device, single photon counter in a wide range of optical wavelengths. So this is the area which I'm right now the most involved in this. But in general, any issues you may have regarding that overlay between optics and superconductivity, that's what is the area of my interest.
Great, thanks. And let's have a round of applause for our panel. And now hopefully we'll have some stimulating questions from the audience. Who wants to be first? Okay.
I have an application, because hearing what you were just saying, just dawned on me. And I address it to you, to Mike, maybe, and also, this is detecting partial discharges in a cross-linked polyethylene underground cable at particular joints, where you're dealing with partial discharges of a few picocoulombs, creating a nano hertz wave or something that comes out. But you're in an environment where there are hundreds of this something that we should look into as a possibility for detecting these partial discharges? In the factory, when the cables manufactured, they're inside a Faraday cage, and so they can find these small discharges. But when you're out in the field, which is what we want to do, real-time online monitoring of systems that are underground, can't get to them, with a superconducting detector of some kind, do something. Anybody say anything about that?
Well, one question is, I understand that this is just a spontaneous event, that you cannot sort of trigger it in any sense. So that's what makes it much challenging. So it's, you look at the, not the counter, but true detector. In terms of, you talk about nanocoulombs, but so it's an emission of what will be frequency range, an emission of pulse radiation, or it really depends on. I would like to convert into sort of my scale what kind of energy that in a single event, what kind of energy is being associated with, because that would be the main issue if the kind of detector we've been working on it may be suitable, or a squid time detector may be suitable. So that will be the question, and that we can talk later. So that's one. The noise issue, of course, if we can somehow gate it, that of course would be the best way to get rid of all the noise. Otherwise, we would need to find a specific signature which would make that event different than the other, if that's possible. But otherwise, if your spurious effects are identical, then you cannot distinguish. And they are as good as the one you'd like to catch to get rid of.
Yeah. Typically, of course, what he said is that you would characterize this, a spectrum analyzer and powered, then you would move on and see if it makes sense. Usually you can do those things.
Larry Smith from Semitech. I haven't heard anybody this morning yet say anything about prospects or speculation for higher temperature superconductors. This was something, about a year ago I read an article, it was written by Matt Beasley, who's kind of well known, where he was actually speculating about what the properties of a room temperature superconductor might look like. And so my question for this panel, the previous panel, is that does anybody see the possibility of actually getting there? Because, and especially in the electronics area, as we get to smaller and smaller dimensions, copper just isn't good enough. And it seems like a very speculative proposition, but you have serious people talking about the possibility of building superconducting wires that would be superconducting at temperatures higher than room temperature.
Okay, would like to take that.
Well, I know Mark Beasley and his talk also first, and in his talk he also questioned whether high temperature superconductor, high means room temperature superconductor, would be any useful. So
right.
that is the question by itself, because although majority of customers hate low temperatures, there are advantages which comes with that. It's low noise and ability to work with very low signals, and means low power. So therefore, if you're talking about electronics application, there is an advantage in operating at very low temperatures, and that means you will automatically be at very low power. That doesn't mean that high temperature superconductors are not useful. They are. And one of the applications, when you look at the systems, all systems now that using superconductivity, they actually heterogeneous technology systems, and which span from 4 Kelvin, or in quantum computing, even from millikelvin up to room temperature. So you have multiple temperatures where you can deploy different technologies. CMOS at the room temperature, and then high temperature superconductors at, let's say, 70 Kelvin, if we're talking about YBCR. Between them, we can put, between, let's say, 4 Kelvin and 70 Kelvin, you can put high temperature superconductor cables. Because cables, superconductive cables do not transfer heat. So there is no heat leakage into lower stages of cryocooler. And they low loss, virtually no loss, and no dispersion. So you can send tiny pulses, tiny signals through these cables from 4 Kelvin, where they naturally sort of have very advantageous environment, to 70 Kelvin, where they can further amplify or convert into optical domain, and so on and so forth. So that's why I would say high temperature superconductors are useful, but not an expense of low temperature superconductors. So you need to look at the temperature as another dimension that conventional electronics do not use, does not use. And in superconducting system, you have, in addition to all other dimensions, you have this temperature axis where you can deploy different technologies and have overall system advantage.
Yeah, Lawrence?
Just one comment. Although high temperature superconductors are wonderful in terms of physics, in terms of applications, especially if you talk about electronics and low power applications, the problem is that, like, for a typical like YBCR, the coherence lasts in the order of few nanometers. So even like 200 nanometer wide stripe is a bulk. So what is in semiconducting industry quite often in nanoscience, here it would be still just bulk material. So if you like to think about nanoscience in terms of high temperature materials, you need to talk about single nanometer, few nanometer type structures. And in general, especially of devices or any other kind of scaled up applications, that's really far away. And that's one of the technological challenges of that structures in other areas regarded as nanostructures here. Or what is in a low DC materials, a nanostructure would be a bulk type device.
Okay.
I'd like to reinforce the issue just raised. There are a lot of hobbyists who will actually go through the torture of removing the heat sink from the microprocessor and pouring liquid nitrogen on it in order to overclock it. And of course, the record, as we know, for things like Intel parts and Opterons, is around 8 gigahertz. Not a bad thing. Now, if we could just figure out how to drop the power circuit so liquid nitrogen temperature was more readily achieved, I think we might have the solution for that problem just raised. But you have to get the power of conventional electronics down quite a lot to make that interesting.
Anyone want to comment? Thank you. Yes.
One thing that strikes me with this panel is that you have digital superconductors, quantum computers, semiconductors, connectors, and photonics all sitting at the same table, which are all platforms. And we talk a lot about how to interconnect them and integrate them and use them in common systems. But it seems that a digital superconductor requires, it computes with a different logic than a quantum computer and the semiconductor. They all need their own algorithms if they're going to be optimized. So in the chicken and the egg kind of question is, where are the algorithm people that think in these hybrid systems like we think? Because we think about the physical connecting of all of these. But I would say, for the most part, people in this room don't write those algorithms, don't think about that logic. how do we connect ourselves with those two? Good question for anybody.
Well, I would say, I mean, clearly it's the aerospace defense contractors that have the thousands of engineers that it takes to deploy a solution. I mean, I think everybody, you can get a little caught up in the manufacturing part of it and think the job is done, but you're right, Dick. I mean, it's an enormous challenge, and I think that the other thing to recognize is that as silicon progresses, it is operating in ever higher electromagnetic spectrums. I mean, the 28 nanometer node can do 60 to 77 gigahertz. So it's moving into the realm that was before only done by compound semiconductors, and so and it'll continue to do that, and it's doing it at a very low cost. So, but you've got thousands of, you've got an enormous momentum behind that. So I think what my point of my comments was that you're spot on. I mean, it's the integration of all of these elements that is where we should be focusing. I think collectively on what are those things that we can leverage off of the mainstream world and adapt it for those aerospace defense contractors who operate in a higher performance arena and hopefully a higher price point arena to help pay for this. But I think if the value, if you can do it, is that you can rapidly lower that price point to open up bigger markets beyond just defense space. And I know in the 80s they used the term dual use, and it fell out of favor. But I think really, it's really here now. I mean, you're seeing that capability being in the smartphone today that is opening up a lot of opportunities for smart cities, smart transportation, things like that. So think of a radar, something that you could, maybe superconductivity could be used for a higher, more sensitive detector of some sort. If you could integrate that and commercialize it on your silicon infrastructure that's out there, whether it's MEMS-based or what have you, I think you've got a real value proposition there that investors would back.
With regards to integration, I'd say that actually with the quantum computing architecture that we're trying to build, we're already looking to integrate many of these other technologies, such as things that Oleg works on. So on the algorithm side, that stuff is still developed. There are quantum algorithm guys who have laid out exactly how you want to do quantum error correction. And so then we need to interpret how do we build the circuits to the actual superconducting circuits to run these algorithms. And then we need to piece together the whole system, which is actually now there's your qubit system, there's your qubit chip, there's your cryogenic system, there's your control, and then there's your readout. And these controls and readouts can actually be superconducting technologies. So superconducting D/A. On readout side as well, we're basically detecting really low energy microwave photons. So again, can we get some type of superconducting A to D converter that would then let us take these digital signals out so that we can then go to the classical computer part, which would analyze the qubit results to basically then feed back into the next step of the error correction. So we're at this stage where this integration is actually going to become a key, and having these links with companies like Hybris is going to be important.
The other aspect, I think, is in terms of algorithm or interfacing and all that, is standardization of these interfaces, and I think that will move things along a lot. Just as in normal computer development, there was TTL logic at one time, and all the standards there propelled that, to the stage to where, large large but powerful computers could be built in the 70s, and then they went on chip and so on. And USB, for example, so all these standards are extremely important in moving the technology along. That has to happen, I think, in this field too. It's going to be a challenge because it takes a lot of money.
Maybe I'll ask a question, just to sort of continue on the discussion from the last panel. And anybody should feel free to chime in, but when we think about any limitations we have on our research or industry coming from natural resources, things natural and maybe not so natural. Liquid helium, we heard a little bit about, it's a big deal right now, at least for me. Maybe helium-3 is another issue, especially Jerry. Superconducting materials, maybe cryogenics hardware, these sorts of things. Good question.
Well, I would say in the device area, our quantities that we use are so small that it probably isn't a limiting factor.
Well, I would say funding is a limiting. Superconductivity is out there. In funding agencies, spintronics is much better than password, or nano anything rather than superconductivity. So it's a considerable limitation.
Well, helium, of course, is a potent material that we all need and depend on. And while MRI people, magnet people already raised this question in the previous discussion, we also need helium. And just give you some points. Just a few years ago, the liter of helium, liquid helium, cost $3, and was 6. Now we pay 12 just because we have a long-term contract.
I paid 15.
But other folks pay 15. So that was, yeah, it was exponential increasing cost, and of course it probably we've heard about some federal some movement in Capitol Hill in order to tackle that, but that would be temporary fix. So something needs to be done, and a lot of helium getting wasted during the exploration, not exploration, actually the mining, extraction of natural gas. So, but oil companies, for them it's not economically interesting to extract liquid helium, just helium. And another thing is conservation. I think now when energy efficiency and efficiency of all sorts becomes very important, I think it's perhaps it's a good time to move towards recycling of helium, and especially having in mind that the New York State company Cryomac is selling liquefier. So it's it's a ready-to-use system which available on the market and can take care of recycling helium with some infrastructure put together. But for Hypers, it's a little bit expensive. For IBM, may not be, but still, if would be some help on the New York State or federal level to proliferate such systems throughout the U.S., it would be great help. It would allow to use resources, natural resources, which are not renewable, I would say, in more efficient way. So it would sort of give second life to helium that we buy, or make it like exponential one.
Yes.
Yeah, a question for Jerry. Do you have any crystal balls or ability to project when quantum computers might be a commercial product that
So I think that in terms of being a commercial product, I can't say, but there are stepping stones towards seeing if that will be realizable, and it's the real useful quantum computer will be when you have a really large scale system with many logical qubits, and that these are not physical qubits, but these are logical qubits in the sense that you have need to have quantum error correction in which you correct a bunch of physical qubits to encode a single logical qubit. And so our current path forward of demonstrating 100 physical qubits is really to test and implement these ideas of quantum error correction. And that needs to be really vetted and studied in order to really scale towards a much larger system for doing universal quantum computing. I think what people often do say is the horizon is around 15 years, but every 5 years you hear 15 years. So I'll say 15 years.
How many logical qubits will you have in your 100
In the 100 qubit
system?
system, you should be able to encode one logical qubit. Well. Yes.
Yeah, a follow-up question to that question. Assuming it's 15 years, there will be a lot of positives to it, as you mentioned, breaking encryption. But have people thought about the negatives that would come with that? What could be the consequences of having it?
I think that with regards to that, I'll let our government sponsors think of that.
Just a comment in terms of breaking code, quantum cryptography is now commercially available and is completely immune to, it's not based on mathematics, so quantum computers have no role in breaking. It's based on quantum mechanics. So that aspect is something off the table. From quantum computing. Yes.
I just want to make a comment about what are some of the controlling factors that superconductivity especially is suffering from. And that is everything is decided based on cost or money. And what I have certainly experienced is that only small companies like MTech or Hypress, even though they don't have enough money, they have the commitment and the long-term interest to proceed. But the leadership that IBM, for example, is showing is not found in many other large-scale industries like General Electric or some of the other companies, because what I found is that innovation is really killed by managers asking questions. Okay, if we're successful here, how much money are we going to make? And so the accountants are now in control whether innovation is implemented or not. And most of the time, unfortunately, if the accountants can't show a return in 2 or 3 years, the project never gets developed. And that's why IBM is pursuing a strategy that I've found is successful in Japan or in Korea, especially now, as we heard this morning. The philosophy there is, let's demonstrate the technology, develop it without worrying about the cost. Once we have successfully developed an application, then we go after reducing the cost. And that's what made them successful, especially in Japan originally in the automobile industry, and the Koreans now in the other electronic kind of items and so forth. They're developing the technology, the innovation that they believe in without worrying about the cost initially. There the accountants are controlling it. And I think until we get over the hump of electing officials that only have a 2-year term and can only see 2 years ahead, or our large-scale financial communities wanting to make a profit in 2 or 3 years, I think we're going to be stuck. And superconductivity, it has been around now for over 50 years. And yet the only measurable successful application is MRI. And there we had the fortunate situation that everything fell into place, and we had a capability to immediately demonstrate a superior system over X-ray, for example. And there was I was involved in some of that, and the opposition we had from X-ray people was enormous. They didn't want to see that develop. They said there's no advantage to it. And now then the radiologists took over MRI, okay, because they couldn't beat it. But the fact of the matter is we need to develop a way to be able to look more than 2 or 3 years ahead, not have the accountants control the success of innovations, but rather having visionary people like MTech and Hypress pursue things.
Well, I would make two comments. First, put in the plug for the Nano College. One, we have one of our 4 constellations is Nano Economics, and it's really designed to train the next generation scientists and engineers to understand this burden sharing. I think when you look at Japan and Korea, you're seeing the government investment is very, very heavy, in maintaining that long-term support. I think what you're seeing here is a different approach that does burden sharing, not with a direct investment, but a collective investment by government as well as primarily industry. Here to again, allow companies to just pay for the incremental cost rather than a single company paying for that long-term support that's necessary to really bring a technology to fruition. I think one of the challenges that often happen is when a company is doing it independently, someone else can develop another technological approach to solving the problem, and then they're kind of cut off from, what are we going to do now type of thing. And being able to reposition that capability for other applications quickly, I think, is important, as well as being able to accumulate the wins or the learning, if you will, as one application is developed, apply that to the next application, apply that. So, rather than squeezing cost out, maybe it's more of a progression of applications that is the approach as well. So, but I completely agree with you. I mean, I think that's the emerging technologies often confront embedded resistance, market barriers, if you will, and it takes a creative, oftentimes with partners, other partners, to try to short circuit that, and it depends on the sector of the application. It can be more, but I mean, I think the reason you look at consumer electronics, a new innovation seems to be on the shelf of Best Buy almost within a month, right? It's because it's as long as it integrates to some common Bluetooth and certain standards, you're out out of the box. But once you move into specialized applications like healthcare, energy, what have you, you're going to have a government oversight. You're going to have these embedded barriers, and it is it's a real challenge.
One last question.
Before getting too excited with the idea of collaboration without market drivers, strong market drivers, Japan is really not a good example. I mean, Japan is actually failed example at this point. I mean, the main concern in Japan is how to transfer all this technology that was produced and nobody wants to do anything with it. And so these Japanese companies are not leading any segment of the market at this point. They have lost all the leadership in electronics, and they have lost the leadership in displays. So I mean, before comparing this model with Japan, you have to consider that market drivers matter a lot in success.
Well, I don't think it's quite as simple. I mean, Japan, I think, has moved more into the enabling technologies, like the equipment manufacturers. Tokyo Electron, for example, is a great example. And there's several. So I think they may not be in the actual device leadership area, but there's frankly very few companies that are in the device leadership area. I think it's more of the better a company can implement transitioning that innovation to an application, they win in the marketplace. And
like the U.S. companies are winning right now in many markets. I mean, Broadcom is leading, Qualcomm is leading, Intel is still leading,
yeah.
Apple is leading in consumer electronics without much collaboration at all. So, I mean,
no, they're collaborating. I mean, I think look, even Intel is now here at the Nano College. I mean, Intel, why are they here? I mean, there was not only technological challenges, it was the business case as well. The industry didn't want to transition to 450.
But Mike, Intel has almost 97,000 employees worldwide, and has how many here?
I don't know what their headcount is, but they're ramping up. And how money they put in here. I think it's about $1 billion, 1.2 billion in investment here. So, no, for the program. Does it matter?
Maybe one last one.
So, I was going to say, you go to market with the system that you have, and we live in a capitalist society. So let's just stop debating that. And now say, where do we go from this?
Yeah.
You know, we've got challenges of innovation is what you're describing more than anything else. And it goes back 200 years. You know, the buggy whip industry in England fought against the development of the automobile very hard to the point where they had regulatory structures that said if you were to drive a vehicle down the road, you had to have someone walking in front of it with a red flag out. That existed until the 1920s, right? So this is not new. You have an embedded incumbents in the field. I think Intel's a great example. That $1 billion, you look at Intel's percentage of revenues they spend on R&D is 20%. It's hard to find an industry anywhere, in any field where a company does that. And they wind up staying however many Moore's Law cycles, what do we have, 75, 76 Moore's Law cycles?
Yeah.
They've stayed #1 at.
Yeah.
That's how they wind up doing it, staying cutting edge.
Yeah.
That's a different problem when you're looking at the early stage. You go back to Edison and Westinghouse. Both of them ran into innovation problems. They ran into financing problems. They ran into all these same things that we're reliving here. It's painful. It's ugly. Yeah, we want to wind up working to get there. We'll do it as well as we can all together, but it's keeping that communication up, I think, that matters more than anything else. I don't know.
Yeah.
You know, you're a scholar of innovation. I mean, what should we do that's better?
Well, you know, I love history, and I often use the example of the oil industry and how did they, you know, drill, get the oil, build refineries, build a distribution system, and do it all in 10 years. And I always give the hint, Rockefeller. They did it with monopoly, right? So you can't do monopolies anymore. So you need a different approach to accumulate the capital and mitigate the risk. And I would submit that new technology development models have to be developed. I think that's the whole idea behind President Obama's NNMI, is that government is now, look, it's not a question of whether government participates anymore. It's done. Now, everybody else is doing it. Government has to be involved with that investment. The question is, where's the investment? Is it going to be on fundamental research, or is it also going to be transitioning that research to volume manufacturing? I think I'm excited because I'm seeing that resurgence, you know, kind of coming across the nation, and I think a lot of it was triggered also by the financial collapse, that now people look at, hey, building manufacturing is actually a way to build wealth and value, and I think I think people lost their way thinking that you could do it with baseball cards and quick real estate, you know, investment.
I think on that note, we should probably wind things down so that we can stay on schedule and have time for lunch and for the afternoon.
Great.
So I'd like to thank all of you in the audience for your attention.